Let f of x be equal to x plus 1 times x minus 2 times x plus 2. And we notice that if you plug in 0, you get 1 times negative 2 times positive 2, that's negative 4. If we were to plug in 3, we get 20. If you plug in 3, you get 4 times 1 times 5, and that's equal to 20. Use these observations to prove that f is negative from negative 1 to 2 and positive from 2 to infinity. These are called test points, and these are used in pre-calculus sometimes for graphing polynomials. So before we actually do the proof, let me just explain how they're used. So here's x and y axes. So let me plot in the axis. So negative 1's here, 1, 2. And we've established that there are roots at, one more root on this side at negative 2. So the roots of the polynomial occur at negative 2, at negative 1, and at positive 2. And so what the test points do is establish where the polynomial is negative. So f of 0 is negative 4. Okay, so that basically means because f of 0 is negative 4, that means the function must be negative between this root and this root. And so the graph has to go something like this. Something like that. I didn't put a bend in there that I didn't mean to put, so let me make it a little bit better. Something like this. Likewise, f of 3 is 20, so out here to the right, the implication is that the function must be positive. In between, if you were to plug in a number between negative 2 and negative 1, you'll find that the function is positive, and so the graph must be positive. And if you were to plug in a test point to the left of negative 2, then you'd find that one test point is negative, which implies that every point is negative to the left of negative 2. So this is a technique used in pre-calculus for students to be able to provide rough sketches of polynomials that does not require calculus. Just simply finding the points and then using test points in between the roots of the polynomial. Of course, when students learn calculus, then they can provide better graphs by exactly finding where the peak is here and where the trough is down here, as well as finding the point of inflection. But as a first step toward curve sketching, sometimes test points are used for this purpose. Okay, so basically the question is, why do test points work? So prove that f is negative between negative 1 and 2, and prove that it's positive between 2 and infinity. So proof. And let's do for part 1, and this will be by contradiction. Suppose that there is a number c between negative 1 and 2, so that f of c is greater than or equal to 0. Well, c can't be a root of f. The roots of f are negative 1, 2, and negative 2, so there can't be any roots there can't be a fourth root between negative 1 and 2. So since f of c can't be equal to 0, it must be that f of c is positive, because it clearly can't be negative. Okay, so also we've noticed that f of 0 is negative 4, but most importantly it's negative. So by the intermediate value theorem, And we are allowed to use the intermediate value theorem because f is a polynomial and hence is continuous. There must be a number t between 0 and c so that f of t is equal to 0. Okay, so f of c is too big, f of 0 is too small, so there must be some point in between the two so that that is just right, so that f of t is equal to 0. But 0 is between -1 and 2. Also, c is between -1 and 2. That means that t must also be between -1 and 2. But t is between -1 and 2 because it's between 0 and c, and it can't be a root. And that's a contradiction. So that implies that f of x is negative for all x between -1 and 2. So that is the first part to prove that f is negative between -1 and 2. Now for the second part, we need to prove that f is positive to the right of 2. Now I encourage you to pause the video at this point and see if you can do it, mimicking the steps that are shown on the screen, and then restart the video to see the proof. Okay, so now let's do the second part of the proof to show that it's positive between 2 and infinity. So once again, this will be by contradiction. Suppose there is a c greater than 2 so that f of c is, that's not a very good c, f of c is not positive, which means that it is either 0 or negative. Well, since c is greater than 2, f of c cannot be equal to 0. The roots of f are -1, +2, and -2. There can't be a fourth root to the right of 2. And so, and that's supposed to be a greater than, not a greater than or equal to. Since c is greater than 2, c cannot be a root. So that means that f of c, if it can't be equal to 0, it must be positive. Must be negative. Also, we've established that f of 3 is 20, and more importantly than the numerical value, that it's a positive number. So again, f is a polynomial and therefore is continuous. And so by the intermediate value theorem, there is a t between c and 3 so that f of c is equal, f of t is equal to 0. F of c is less than 0, f of 3 is greater than 0, so therefore there's got to be a point in between c and 3 that is just right, and so f of t must be equal to 0. but t is greater than 2. If c is bigger than 2 and 3 is bigger than 2, then anything between c and 3 must also be bigger than 2. So f of t cannot be equal to 0. Providing the contradiction. So f must be positive. On the interval from 2 to infinity. And that's the end of the proof. And similarly, the logic would apply for the other intervals from negative infinity to negative 2, and also from negative 2 to negative 1.